All right, good day, class. And as we get my pen and mouse going, let's see, it's over here. Whoops, you can't see it, but I can. All right, there we go. So we're going to talk about section 2, which is all about acceleration. Now, this is going to be a very deep and involved section, just because of the way we can manipulate the equation, the acceleration equation, to solve for various types of data that were presented. And this is why everybody kind of hates this part of the chapter, because there's a lot of equations involved. Now, a lot of these are going to be proofs, and on Edpuzzle you have the actual how to determine the answers for all these, have examples. But what we're going to do is show you a proof and how these things work or where they come from. And that's what you need to know, is that a lot of professors in college will do this. They'll give you a problem and they'll give you an equation and say, okay, if we manipulate this equation, substitute this one for what we talked about 2 days ago, and here we go, another equation that you need to know. And they'll give you proof, figure out where it comes from. And this is important because we're going to do the same thing. So I'm giving you a taste of this. All right, so let's go ahead and start with this. We're looking at acceleration. So we're looking at acceleration here. It's defined as a change in velocity as a function of time. So there's those little deltas right here. This means the change of. So this could be Vf minus Vi and Tf minus Ti. Remember, final is always first and then minus initial. As with velocity, it has a direction of magnitude. Because you can have a positive velocity, and if you're slowing down, that means the acceleration is negative going the other way. This is going to become important when we deal with forces, but since we're dealing with motion, we want to make sure you understand the forwards and minuses. And remember, if we have a number line or a two-coordinate plane, this going to the right is positive, going to the left is negative. Going up is positive and going down is negative, and this is by convention. So when we graph velocity versus time, we're going to have two sets of graphs. So we're going to have one where it's a straight line. So the slope is going to be constant, it does not change. This means that acceleration is constant and we have a constant acceleration. Now, there's another type of graph that you see it goes up, it goes down, then it may go up again. This is the slope is variable. And this means acceleration is not variable. So acceleration changes. Now, in physics, we've got to deal with both. But in this class, we're going to deal with this, where the acceleration is constant. Excuse my squiggles. This you need calculus to solve when acceleration changes. So the red line you need calculus, the purple line you just need algebra. So we're going to do another, but everything we're going to deal with is when acceleration is constant. And so what we have here, you notice we have a little table. This is our initial velocity. If the initial velocity is positive, acceleration is positive, we're speeding up. The magnitude of our vector is increasing. If both are negative, initial velocity and acceleration, our final velocity is going to be higher in magnitude. It's speeding up. If one's positive and one's negative, that means the magnitude is decreasing, either slowing down in the positive direction or slowing down in the negative direction. If acceleration is 0, we have a constant velocity. It's not changing its velocity, so it could be the positive or negative. We don't care. It's not if the velocity is not changing, the velocity is going to be constant. That means it's moving. If velocity is 0 and acceleration is either positive or negative, the magnitude is increasing, speeding up from rest. Either going more negative or more positive. And 0, 0, that means the whole thing, our whole object is remaining at rest. Again, that's something important to know. So you got all these conditions. Guys, you guys know this. You've done it so many times in a car with your parents, or if you're driving, you've done this. So this should be fairly easy. Okay, let's look at this equation for problems. Displacement with a constant acceleration. So we're looking for, what we're going to do is we're going to do some manipulation of this. Here's our velocity, delta x over delta t. Now, another way to say this is our average velocity. Another way to look at average velocity is adding Vf and Vi together, then divide by 2. This is what we mean by average velocity. It's the same thing, but just two different ways how to get there, two different data sets. And if Vf is not 0, you use this. So what we're going to do is, looking at this, know that V average, we take these two equations and equal each other, and this is what we did here. So delta x over delta t is equal to the average velocity, which is Vf plus Vi over 2. Then, guess what? Move the delta t over, multiply both sides by delta t, the time, and now we have that delta x, our change in x, our displacement, is equal to the average velocity times time. Everybody's going, well, that makes sense. But the thing is, guys, if this is a non-zero value, you got to figure out what the average velocity is. And this is why we introduce this equation, because Vi is not 0. That's something I want you to be aware of. All right, so we have a velocity with a constant x, constant a. So here's our velocity equation, change in velocity over change in time. If we don't know that, it's Vf minus Vi over change in time. Remember, usually change in time, Ti is always 0. So we're going to move multiply both sides by delta t, and we're going to get this value here, where a times delta t is equal to Vf minus Vi. Guess what happens? Let's add both sides over to this. So another way to write this is a delta t plus Vi is equal to Vf. Both these equations are the same. All I did was put Vf over to the left. But this is the equation we're going to be using for, and this is in set 4. Set D, excuse me. Acceleration times time plus our initial velocity, sometimes it's 0, sometimes it's not, is equal to our final velocity. And this is where you have to read the questions carefully to figure out, hey, is this going to be positive? Do we have a value here, or is this going to be 0? If it's 0, that goes away. That makes everything easy. If not, you got to compensate this equation for Vi. Now, displacement with constant a, constant acceleration. Now we're looking for displacement. So, remember, the change in x, displacement, is the average of our velocities plus delta t. And so, what do we have here? So, we're going to change this to say Vf, coming up here. We're going to take this equation. This is from our last slide, where final velocity is equal to a times delta t plus Vi. So substitute that into this. So we have the change in x is equal to displacement is equal to our acceleration times time plus velocity, initial velocities, over 2 times delta t. Well, we can reduce this down. So our displacement is equal to 1/2 a times change in time squared. So basically what we're doing is we're taking a delta t times delta t plus 2vi times delta t and divide by 2. Then we're just kind of separating that out, and this is where the 1/2 a acceleration times time squared comes in. Acceleration times delta t squared. The 2's cancel, and vi over delta t. So this is problem set E, just using this equation. So that's displacement with a constant acceleration. You're given the acceleration, you're given time, and you're given the initial velocity. If the initial velocity is 0, this makes this easy. And then the final velocity, Vf, with any displacement. So we know the displacement, and we know we're looking for final velocity. We have to know the acceleration, or we can determine the acceleration. So if we know the displacement, or any of these values, 2a delta x plus vi squared and vf squared. How do we get this? Well, we take this, 2 delta x over vi plus vf, and that is moving this over, and then dividing by vf plus vi. So we want to isolate delta t by itself. Then we're taking this equation and substituting delta t. And we'll have this mess. Vf is equal to vi plus a 2 times delta x over v plus vf. Subtract this, so we get vf minus vi. And then we're going to multiply both sides by v plus vf. And this is what we get here. Now, this condenses down to this, where it's vf squared minus vi squared is equal to 2ax. Move the vi over, and then you get this equation at this point. Again, with this, vi is usually 0, so that can go away. You gotta have this set of data. You're looking for one of these variables: final velocity, initial velocity, acceleration, or displacement. If you got 3 of these, you're going to use this equation. And let me go back. If you have change in time, vi, acceleration, and displacement, one of these, you're going to be using this equation. So you got to realize which equation to use based on what's given to you in the problem. Go back to this slide. If you got acceleration and 2 velocities and time, you're going to be looking for this. Realize what data set you have. This is why we practice these problems. And with this, velocity and displacement. I hope, as I go forward back to the end, I hope this is what you need. Have a good day.